in this video we want to talk about the motion of particles through fluids. All right. And more particularly, we're going to talk about the concept of sedimentation. For sedimentation, imagine that you have a tank, okay, filled with some liquids and some particles. And basically what happens is that after some time, wait enough time, and those particles, they're all going to fall at the bottom of the tank. And an application of that will be in water treatment, where sedimentation is physical treatment that utilizes gravity to remove suspended solids. Okay, so we have for that settling basins, clarifiers, which are constructed for this purpose. What we want to discuss is the mechanism of particle motion. And so we're going to consider just one particle. All right, let's try to draw it well. Okay, that's our particle in our fluid. And we're going to look at all the forces that act on this particle in the liquid, in the surrounding environment where it is. So basically, there is the force of gravity, so remember this is going to be one particle. So the gravity force acts on our particle. There is also, since it is immersed in a liquid, in a fluid, there's going to be the buoyancy force. And as it's moving down, like towards the bottom of the tank, there is a drag force that opposes the fall of the particle. And what we want to do next is express each of these forces. So let's start with the gravity force, which we will call Fg. So the force of gravity is just expressed as the mass of the particle times the acceleration of gravity. Okay. And the mass of the particle, we can also write it as the mass density times the volume of the particles times g. Okay, so m particle is expressed in kilogram, rho p, that's the mass density, in kilogram per cubic meter, and v, or maybe I should just, to be consistent, I will call it vp, that's the volume of the particle, and that's expressed, it's not in cubic meter, but I mean the SI unit will be, yes, cubic meters. Alright, so we've expressed our gravity force. What we want to do next is express our buoyancy force. So the buoyancy force, which we'll call here Fb, is expressed in a similar way, except that we're not going to use the density of the particle, but the density of the fluid, since that force kind of tell you that an equal volume of fluid, an equal mass of fluid is going to be displaced. So the only new quantity here is the fluid density. Which is also expressed in kilogram per cubic meter. Okay, and finally our drag force. So drag force, as we saw it before, it's going to be expressed as Fd as a drag force coefficient, Cg, times AP, where AP will be our projected surface. We'll come back on this a little bit later, times 1/2 of the fluid density, and we have the square velocity, so that's kind of a kinetic energy term here. UP, so that's the particle velocity, and that's actually the average particle velocity to the square. Okay, so that's particle velocity in meter per second. This one is the projected surface. And this guy CD is a drag coefficient. And rho F is again our fluid density. Alright, and what we want to do is determine what we call the terminal velocity. How to determine the terminal velocity of the particle which we will call UT. I said the average terminal velocity to be consistent with the average UP. So first we need to realize that when the particle reaches UT, when the particle velocity reaches the terminal velocity, then the particle becomes still. It's no longer moving anymore. Alright, so that particle is going to be in a state of basically equilibrium. It's going to be completely still in the fluid. So not falling, not raising, just still. And from there, you can simply write that all the forces that are applied on that particle equal to 0. Once we recognize that, then we take our three forces, we have our gravity force, the buoyancy force, and the drag force. And we're going to write that force balance in the z direction. So take the z components of these forces and basically write that the sum of these forces equals to 0. So if we're taking, well, you can take z positive upward or z positive downward, doesn't change much. We will still have AFG, force of gravity, is balanced by the buoyancy force and the drag force. All right. Or simply AFG minus AFB minus AFD equals to 0. So in the z direction, well, anyway, all these forces only have, in this case, a z component. So it's going to give you rho p g vp. So that's for the gravity force, minus rho f g vp minus cd ap times 1/2 of rho f up average square equals to 0. Okay, so now we want to find ut, so we're going to call the velocity of the particle ut, and we're going to solve for it. So we'll have cd ap 1/2 of OF ut average square equals to g vp, and on the other side of the equation we have rho p minus OF. So from there we'll have ut equals to the square root of, at the numerator we'll have 2 g vp rho p minus rho f, and at the denominator we're going to have cd ap and finally rho f. So that's one expression. That's one expression for our terminal velocity. Of course, we can try to go a little bit further, and what we're going to look at now is this term AP and that term VP. So VP, we know it's the volume of the particle. So the volume of the particle can simply be expressed as pi dp cube divided by 6, where dp is the diameter of the particle. Now what about AP? So AP is the projected surface. So the way you need to look at it is, it's not the surface of the sphere, the surface of the particle, but it's the projected surface, which, if we draw again our particle, let me try to draw again our particle. Oops. Circle, okay. This is our particle, and it's falling, right, in our tank. So that's our tank, and basically the projected surface in this case will be the surface of a disk. right? You need to project the sphere here, and you get a disk. So that's surface of a disk of similar diameter. Oops, sorry for the typo. Similar diameter. Okay, so that's our disk. And the diameter of the disk is also dp. So what's that surface then? It's simply pi dp square divided by 4. This is why you gotta be careful. It's not the surface of the particle, it's the projected surface area of the disk. And then we can also look at our drag coefficient here, Cg. And we know that in laminar flow, Cd is going to be expressed as 24 over the Reynolds number, REP. So that's for laminar flow. We have that linear relationship. And REP equals to fluid density times a length scale, which here will be the diameter of the particle, times a velocity, which will be our terminal velocity, and divided by mu. So now we can get back to our UT and express it simply. Using the expression of VP, AP, and CD. So we have 2 G, so ways of VP. VP equals to pi dp cube divided by 6. Then times rho P minus rho F divided by our CD, which is 24 divided by rho F dp ut divided by mu multiplied by AP, where our AP is pi dp square divided by 4, and times our fluid density. And now we can simplify everything. So let's look at all these terms. So here we have dp cube at the numerator. At the denominator here we have dp squared divided by dp, so we have dp. So eventually here what remains is just a dp square. Okay, so we're going to write this way. dp cube dp square. All right, so this becomes 2, and we can cancel out those terms. Then we have rho F divided by rho F. So rho F divided by rho F, we can eliminate these terms. Here you have 24 divided by 4, which will give you 6. So you got 6 divided by mu. Okay, we have here 6 divided by mu. And let's not forget that we also have our ut right there. Right, so we've taken care of these terms already. And at the numerator, we still have 2g, so the pi vanishes. And we also have a 6th here, and we have rho p minus rho f. All right, and then, well, you can take the square of that. It will be probably easier for the moment. So we're going to have ut square equals to, so we drop the square root. We have 2 over 6 over 6, so that's going to be 2 over 36. So 1 over 18 basically. We have g here, dp square, rho p minus rho f, and we have our ut that comes back here, and I made a mistake right there. Sorry, it was ut divided by mu. So we had our ut right here, and we had our mu on top here of the denominator, which means that there the mu remains at the denominator, so the viscosity basically. And so after your ut becomes g dp square rho p minus rho f divided by 18 mu. And that's basically the expression of the terminal velocity, which is a very important parameter that we can determine in the motion of particles of fluids, basically during sedimentations. So you see, it depends on parameters associated with the particle itself, so how large the particle is, but also how dense it is, and with the fluid, since we have the expression of the fluid density, and we have also the viscosity of the fluid. Okay, so the more viscous your fluid is, and of course the lower the terminal velocity is going to be.